practice based on MOSFET current mirror and MOSFET inverter. This is my new video. Right, in this first write the questions based on this. Chapter number 4. Chapter number 4 for EC students. Chapter number 4 EC students. Chapter number 4 EC students. The questions are based on question number 3 we can do it based on current mirrors. Question 5 CMOS inverter question. Question 6 we can do it. Question 6. Next to question 7. Question 10. Question 10. Question 11. Question 13. Question 15. Question 18. Question 19. T1 question. T4. T1, T4. Generally, whatever the questions we are practicing in chapter 6 for electrical students, nearly all these questions are same. So they kept the same questions actually in both our books. So you can write here, question numbers are right, but both the same content. Just slightly one or two questions number changes, but all are the same questions in this topic. Electrical book maybe you can see all these questions. Just only number slightly changes. Here question number 3 here. Question number 5 is there. Question number 6 is there. Question number 9 is there. Question number 9. Question number 11. Question number 13. Question number 16. T4. Maybe one or two questions slightly different from this electrical EC book, I think. Let us see first we cover these questions. Anything is extra, we'll try to see that. So I think first we'll give the brief discussion of short notes. I thought that it is not required, but it became a hobby for us to write the short notes. Let us write. So that better we can recollect whatever the points we learn, just we'll recollect the points. Okay. Then we can start the problems based on this. Okay, maybe it may go to 6:30, 7. We'll finish this class and we'll stop it. Okay. So let us have small workbook, or I can say short notes first. So with this chapter 4 and chapter 6 electrical students, we have been completed this issues then. Okay. Samresh, don't say first electrical, don't say me. But here more questions are there compared to this. That's why EC book I'll do it. It will cover the first main questions for you. Because electrical students go, MOSFET questions has not came from 10 years onwards. There all questions has been copied from EC book only. Because previous 10 years they asked BJT questions, they are not asked MOSFET questions. From 2019 onwards, they started MOSFET for electrical students. That's why this workbook is being copied from EC book only. That's why anything is okay here. First you study karo. Because maximum questions you are getting from EC book. Maybe some questions are missing actually. Here we have more questions compared to this. So cover this one first. That is beneficial compared to teaching electrical first. Okay? That's why I'm considering EC book for this. First EC book cover the electrical, I think you can take a work on that. If you have any one or two problems are new, you can try to start doing the practice by yourself. Okay? Any new questions are there? Maximum new questions are not there. Similar questions, maximum. So let us have some summary, whatever we studied till now. Let us have a summary based on this. Just give me some 15 to 20 minutes to give the summary. Then we can start doing the practice. So please note on it. Yes, we'll have to practice what we done till now. Current mirrors, one knowledge I have explained, and one more is we have is inverter design techniques. Let us have one time revision on that points. So let us see the revision now. First we have is MOSFET current mirrors. Short notes you can write reading. Short notes. First point is simple current mirror we have understood. Simple current mirror. Simple current mirror. Whenever we study this point, what is the knowledge we got is the current transfer ratio, your I0 by I reference. The current transfer ratio formula we got it as W by L2 by W by L1 is the knowledge we got if lambda is equal to 0. If lambda is 0, this is the relation we practice. Second relation is I0 by I reference is equal to W by L2 by W by L1 into 1 plus lambda times VDS1 divided by 1 plus lambda times VDS2. Because in simple current mirror, VDS1 is not equal to VDS2. But if you come to the second one, Wilson current mirror. In Wilson current mirror, the formula became again same like this. I0 by I reference. I0 by I reference, we got answer as W by L2 by W by L1. Where here lambda is not equal to 0. We have achieved this concept because VDS1 we made it as VDS2 in this concept. This is the summary of your current mirrors in MOSFET. This is the summary. This is the summary here. Current mirrors okay. This is about simple current mirror and Wilson current mirror formulas in the class. Okay. Let us move to the next what do you say inverter questions. Inverter concepts are like this. Point number 3. What is that NMOS inverter? NMOS inverter with passive load. NMOS inverter with passive load. Just we need only graphical knowledge, not more than we require. This is VIN, this is V0. So there is some threshold voltage. From that we have some boundary line. So up to threshold voltage, we are getting here VDD. After that we have parabola fall and nonlinear falling like this. So here M is M1. Here M is cut off you can take. M is cut off. Here M is current saturation. Here M is 5. So this is the knowledge we got in passive load technique. Okay, the graphs are important to keep in mind. NMOS inverter with passive load. If I go for fourth one, NMOS inverter with active load. NMOS inverter with active load. If you want NMOS inverters with active load design, you can have like this. This is VIN, this is Vout. We have again VT line. Here we have some drawback, that is VDD minus VT. Because of active load, we got minus VT there. And we have some linear line we got. After that we got non-linear line. So here M1 will be cut off. M2 is in current saturation. Here M1 and M2 are in current saturation. Here M1 is in triode and M2 is in current saturation. So this is the knowledge we got about NMOS inverter with active load. I'll just magnify it. So up to here you completed. Only one thing is CMOS, last step. And somebody is asking me the derivation of VDD by 2, how it came, that I'll explain the last short notes in a clear manner. Then mathematics I'll repeat once again. I'll avoid the confusion for you. PMOS equation, how to write, we'll see. A small derivation I'll explain once again. So this content is very small content it is. Hardly you can see in one slide we covered the content what we have been studying till now. This complete content will help us to do these questions called inverter questions and your current mirror questions in the class. So don't take much pain about these topics. Always remember, NMOS always start with cutoff first. After that, it will go to current saturation. Lastly, it will go to triode. That is NMOS techniques. If PMOS also comes, then logic is opposite. It will start with ohmic, next it will go to triode, next it will go to current saturation. Opposite technique. Repeat thus the derivation. I'll try to explain in the fifth point by drawing the graph of your current CMOS inverter graph. I'll draw it and I'll show you the derivation once again for you. So please complete it. The last one, let's see. The last current mirror. Yeah, sorry for that. Here by mistake I have written, some student has been observed. It is 2 here, this is 1. Sorry for that. It is 1 plus lambda into, here VDS2 you have to take because W by L2 it is, here VDS1, you have to change that here. Thank you very much. Who is this given this point? So thank you very much for correction. Observation is good, thank you. So let us see the fifth point, final one. The final one is CMOS we have studied. CMOS inverter. Just it should become a hobby, this graph every time for you. Should be like a hobby for you. See the graph, it's very easy to remember. This is VIN, you take this as Vout. How to practice the trick you can see. First you write this boundary line, for example. I'm writing here, this one line here. This for NMOS line. This for NMOS, remember this point. From y-axis if you intersect, that is coming for PMOS line. One is for NMOS, one is for PMOS. First PMOS will come, then NMOS will come. Okay? So how you got the story? First, up to threshold voltage, you just write a marking here, saying that this is the first point, point number 1. First area is 1. The next we'll try to have non-linearity falling like this. This you take it as second area, falling number 2. The next it will fall linearly I'm telling. And exactly, it has to fall at VDD by 2, that is our O. This is point number 3 you take. Last one we have is point number 4. These are the 4 points. Nicely write the points side by. Your M1, you consider it as NMOS here, indication is NMOS. M2, you consider this as PMOS. These are indications I have taken. M1 is your NMOS, M2 is your PMOS. 2 indications I have taken. Now start the regions now. Point number 1, what this region indicates is your M1 will be cut off here. That is NMOS will be cut off, but M2 will start with ohmic. Like this you can just blindly remember these regions so that the problems are easier to do in CMOS. Today you'll understand when I'm doing in workbook how the question they'll ask, how I deal the problem you'll understand. So this point is very important. Initially it started with cutoff M1, M2 is started with ohmic effect. The second point, area number 2, area number 2 is M1 will go to current saturation, but M2 will go to triode. Because of the ohmic it will come to triode. It will not go to current saturation immediately. Next point number 3, it is M1 will be in current saturation, M2 is also in current saturation. M2 is also in current saturation. Next, the fourth one, your M1 will come to triode, where M2 will come to, M2 is already in current saturation. So this is the game actually. The regions you have to keep in mind. Okay, examiner how they'll ask the question says, suppose here VDD is there. Questions kaise baat karte means, they'll ask you VDD by 2 to VDD in between. M1 is in which region, M2 is in which region. Like that they'll ask questions. If you have this type of knowledge, telling the answers are very easy. In between VDD by 2 to VD, what will be there? I think current saturation you are seeing, correct? VD2, VDD by, exactly at VDD by 2, you have current saturation. But when you are in between, your second point will come, that is, M1 will be in current saturation, M2 will be in triode. Below VD, what happens? Like this, you answer the questions. Okay? These questions are very easier actually. Now we'll see the simple proof again, where we have got some confusion. I'll avoid the confusion by doing derivation once again. Sorry. First of all, before doing derivation, a small technique I'll tell you. See here. One is NMOS, one is NMOS, one is PMOS. One is NMOS, one is PMOS. 2 techniques I have taken. What is the generalized expression here is VGS, VDS is equal to VGS minus VT. This is the formula we have for NMOS current saturation relation called boundary condition. So this is a boundary condition where you can go to triode to current saturation to triode region. The same equation here also I have taken. Both sides I have taken same equation. But slightly how I'll make it different, the formula, you can see. This formula, how I'll change this formula slightly means, here I'll add now minus sign on both sides. It will become minus VGS plus VT will come. Just I have thrown minus on both sides. Then I have seen that this notation, we can write it as VSD we can write. That means whenever you said here, VDS is positive in the class, here VSD will be positive. That means opposite notation technique. We will convert that notation opposite, they'll have both signs will be same. So no confusion will be there for you. So this answer you write it as VSD, this minus VGS, you write it as VSG. You can see the trick. Here VGS is positive, there VSG will be positive. If you write VGS, what happens? It is a negative value. We are getting confusion on that. So why can't you convert into the opposite style now? And you got this answer as plus VD. Plus VD. But VD, now you apply the sign. It is minus. So you got this answer as VSD is VSG minus, you keep it just modulus here. Why the modulus I kept is, now whatever the sign you do, it is minus only. So this is the style. This is NMOS equation, that is PMOS equation. You can convert nicely like this. Now derivation when you do, you don't have any confusion now. Now if you apply this concept, ID1 is equal to ID2 in point number 3. I'm applying point number 3, that is M1, M2 are in current saturation. Okay, your M1 and M2 are in current saturation. Current saturation. This is the formula we apply. Now can we take this equation here? Therefore, Kn into VGS minus VT whole square will take this side. Here Kp into VSG minus VT whole square will take this side. Nicely we have written with the opposite notations. Now sign technique problem will not be there for you. Kn Kp will take it equal. Kn is equal to Kp will take. So they will be cancelled in the class. And square if you remove, it becomes VGS minus VT. It will become VSG minus VT. So these two answers you can cancel it. Threshold voltage if you take same, you can cancel it. So what is VGS here is your VIN. What is VSG in the problem previously we have is VSG means VDD minus VIN. Now 2 VIN is equal to VDD. Then VIN will be VDD by 2. So this is the answer. So one more time I have done it, you can see the sign techniques. Don't confuse me, trick you have to do like this. So that sign confusions are gone. Previously that sign problem we got, correct? Because properly if you write notations, you will get correctly the answers. So who has not understood previously, let us understand with this derivation. Okay? In the short notes we got again the proof for it. So with this friends, I have been covered the total theory part now. Now I attack the problems one by one. Let us start. 1 hour within 6:30 we'll finish the total problems now. By 6:30 we'll close the matter. Yashwant Sahu, here negative signs क्यों apply here? Don't ask like that. PMOS में sign से ना हमको. If you say here VDS positive, here VDS is negative. Is it correct? Sign different than here. VDS positive for NMOS, then VDS negative for PMOS. Therefore, when it is negative VDS, then you have to apply this total formula. I change it into that fashion actually. I just moved it into sign techniques. Whenever you have this total sign, here minus, here plus, this equation same. Just mathematics change करो balance करो concept को. So minus VDS को VSD बना दिया, minus VDS को VSG, minus VD थ्रो किया. Statement have created like that. Okay? Why you have taken minus? Stories don't ask me यार. हम balance करके कर रहे problems. If you don't balance like that, previously derivation में confusion आ गया हमको. Answer नहीं आ रहे. So sign technique we apply like this. So whenever you have any confusion, why can't you write this statement in NMOS and this statement you write in PMOS and just balance it? You'll get the correct way of answers. Only sign I'm changing the technique. Because of signs difference, confusions are coming for it. That's why balancing here my concept. So please start doing problems. So complete कर दीजिए problems. So that today work will be completed. Tomorrow, freshly we'll start our amplify questions, amplify concepts. Let us start. Let us start our journey on the problems. Question number 3 in workbook you can see easy book. Everybody can answer that question. Okay. My help is not required for that question. Question number 3. Everybody can do that problem. Everybody can do question number 3. Bose already started working. Is giving the answer D. Bose is telling answer is D. Bose, how you got D here? Bose को D कैसे आया? समझ में नहीं आ रहा मेरे को. So let's start. Why Bose is getting D here? So easy book. I'm solving the order. Question number 3. It is just looking like a simple current mirror. Correct? It is just looking like a simple current mirror. We have an I bias here. This is VDD. He's asking some IX here. This is short. This is not more than simple current mirror tips. Simple current mirror. You take this as simple current mirror. Okay? And he said that M1, M2 are in current saturation. So why can't you write here IX by I bias? This two ratio, current transfer ratio, is W by L2 by W by L1. Apply the formula W by L2 by W by L1. In the problem he said that both M1 and M2 are identical to each other. When M1 and M2 are identical, M1 and M2 are identical. If both are identical, your W by L2 will be equal to W by L1. Both are equal. Then answer will be IX will be equal to I bias. So you can see that this is my answer. B is the answer, correct. Bose has corrected the answer, great. Option B will be the correct answer. It's a simple current mirror problem. Only thing is this formula based questions. Easily you can do it. Next question number 5 we'll see. Question number 5. It's a CMOS inverter question. CMOS inverter. CMOS inverter he has given. PMOS one side and another side. Another side. You have 2.5 volts. This is ground. volts. This is a CMOS inverter question. He's asking you, what is the current I here? What is the current I? And he has given K and Kp both are same. In the problem he said Kn is equal to Kp is equal to same. Kn is equal to Kp is equal to 40 microampere per volt square. But K and Kp he has given as only nu Cox W by L up to this point. He has not given half extra, he has given only nu N Cox W by L. The values are same for both the cases. And threshold voltage is also same. Threshold voltage is same as 1 volt he has given in the problem. Threshold is same. Okay. If you see here, this is VGS, this is VSG. If you take like this answer is also coming 2.5. This answer is also coming 2.5. That means you are in the center of CMOS. VDD by 2. That means your input is exactly equal to VDD by 2 you are. When the input is VDD by 2, in the graph we studied that you are in M1 and M2 will be in current saturation. So M1 and M2 will be in current saturation. That is decided in the class. M1 and M2 will be in current saturation. So if you find out this current, both are same. Any one current you can find. Suppose I find NMOS current. Therefore K is equal to Kn into VGS minus VT whole square. We can solve this one. But here please keep in mind, half is there extra. Half should be there because only Kn means he has given nu n Cox W by L. But half extra is there in the formula. So half into Kn you write according to the given data. So half into Kn is 40 microampere per volt square into VGS is 2.5 minus 1 whole square. So you find out this answer. It is a 20 microampere per volt square. It is 1.5 whole square. How much is coming? Yeah, Satyam. Okay. So what is the answer? So 45 microamps we are getting. 45 microamperes. So we are getting 45 microamps for this question. Just I identified that both the transistors are in current saturation because they are in the center. So completed concept. So option C is correct answer. So question 5 is completed and question 3 is completed in the concept. Yeah. 2 problems we have completed. Let us move to the next question. 6th question, try to solve. Question number 6. Let us solve 6th question. Question number 6. Question number 6. He has given here MOSFET. 2 MOSFETs he has given. This is W by L, he has given as 1. This is W by L, he has given as 4. This is 6. And this is 5. This is about Px. These questions are very popular in exams, in GATE exams. So don't feel tough, they are very easy questions. The only thing is, you have to identify this MOSFET is in which region, this MOSFET is in which region. First you identify it. Then what I'll do is, ID1, ID2 currents, I'll make it equal. Then we'll find out the parameter there. The unknown parameter is Px, we'll find out. Very simple questions there. First understand, okay, which transistor is in which region. You take this as M1 for study purpose. You take this as M2 for understanding purpose. Can I say that this transistor M1 is in current saturation? Perfectly you can tell because there is a short. Because VDS and VGS both are same. Seeing the board you can tell. M1 is in current saturation. But M2 is also in current saturation. How you can say that? By seeing how I said is, this is your gate voltage, this is your drain voltage. Whenever drain voltage is greater than gate voltage, then also you can tell it is in current saturation. When the output voltage is more than the input voltage, we can call it as current saturation. When output voltage is less than the input voltage, we call it as triode region. Okay? So seeing the board, I understood both regions are in current saturation. So I can write ID1 will be equal to ID2. So both the current should be same because they are in series. Correct? So ID1 current we can write as half into UN Cox W by L1 into VGS minus VGS1 minus VT whole square should be equal to, this is VGS1 you can take, this is VGS2 you can take, is equal to half into UN Cox W by L2 into VGS2 minus VT whole square. You can do like this. Both will be equal. So I think this total is same given in the problem. So half into UN Cox will be same for the problem. Both they have been same. Threshold is also same they have been. VGS1 here is nothing but Vx. Vx minus 1 whole square into W by L1, we'll take it as 1, is equal to W by L2 is 4 into VGS2. What is VGS2 here is 5 minus Vx is VGS2. So 5 minus Vx minus threshold voltage is 1 whole square. So Vx minus 1 is equal to square root of 4 is 2 into 4 minus Vx. The square root tablet, therefore, so Vx minus 1 is equal to 8 minus Vx. Okay, so how much is coming you can see? 8 minus 2x will come here. 8 minus 2Vx. It will be 3Vx is equal to 9. So Vx will be equal to 3 volts. Like this beautifully you can solve this type of questions. Sometimes in the exams, they'll give one transistor in current saturation, one transistor is in triode. Then you have to equate 2 different equations. Okay? Then unknown term, you have to solve it. These are beautiful questions. Everybody can do it, these questions. Question number 7 is the next target. Question number 7, first bit try karo. Question number 7, first bit. Without touching the pens, you can tell the answers. Because of the knowledge of the inverter techniques, straightforward seeing the problem, you can get the knowledge of what is the option for that. There are 2 bits they ask, first bit try to solve it. First bit, try to solve it. 7th question, first bit. CMOS has given for small increase VG beyond 1 volt. Means threshold voltage is 1 volt. It just beyond 1 volt you apply. Then what will be the following? Can you think? Logically what happened in your graph. If you are crossing beyond the threshold voltage, 7th question I'm telling, beyond the threshold, what happens? M1, that is NMOS, will go to current saturation. Okay, just it will get on and it will go to current saturation. But M2, which is PMOS, cannot go to current saturation because it will start from ohmic and it will go to triode. I think the problem is straightforward. NMOS will work in saturation, M2 will go to triode. Straightforward answer for it. Okay, therefore, question number 7, first bit का knowledge क्या है? Your V input suppose slightly greater than VT, who will say like this? In CMOS. What is the story of this? CMOS. Your M1, that is your M1 will go to current saturation. M1 will go to current saturation. And M2 will go to triode. This only we studied in our CMOS techniques. Maybe this is your point number 2, which we studied in short notes. Point number 2 in short notes. So M1 will go to current saturation, M2 will go to triode. Without touching the problems, we got the answers. What about the second bit? He said that in the second bit, if VG is 1.5, use the appropriate current relations and calculate the output is asking. If VG is 1.5 is slightly greater than what? Is slightly greater than 1 volt, which is threshold voltage. That means we understood already M1 is in current saturation, M2 is in triode. So ID1 will just equal to ID2. So that is not more than this relation you apply in this case. M1 is in current saturation, so half into nu n Cox W by L. He has given different W bells or same W bells? Same W bell he has given. Half into nu n Cox W by L, VGS minus VT whole square. This is one relation, which comes under current saturation. This is current saturation. Should be equal to triode region. Triode region formula is mu p Cox W by L, VGS minus VT into VDS minus half into VDS square. So this is called triode. This is current saturation, that is in your triode region effect. Okay? So current saturation, this you can keep it as a triode region effect. So one is in current saturation, one is in triode. So Anupam Das, you may keep at 3 volts also, there is no difference because he said VT is slightly greater than the PMOS will work like that only. Okay? There is no much difference if I keep 3 volts also there. It will give the same impact. Don't worry about the 3. 3 is only bias he has done it, gate. So don't get tension about 3. So current saturation, this will become triode. If you solve this problem, you will get some VGS answer, quadratic equation. You will get some value V0 square with respect to V0 square minus 8 V0 plus you can have some 15.25, something you will get like this equal to 0. You will have a quadratic equation with V0 expression. Okay? You substitute these answers in terms of V0, you calculate these answers, you will get a final answer like this. This answer will get 2 answers for you. One is 4 plus root 3 by 2 quadratic method or 4 minus root 3 by 2 will get. So 2 chances will get. 4 plus root 3 by 2 one answer will come. Another answer is 4 minus root 3 by 2 will get. Exactly this answer is 4.866 will come and this answer will be 3.134 will come. So now you have to tell which is correct answer. 4.866 will be good answer for it or 3.134 will be good answer means you are telling that you are in triode region. Triode region means what? VDS millivolts slightly has increased to the triode region effect. So that means this answer, whatever you are seeing, the maximum is 5 volts. 5 volts you are bringing close to the value which are coming close to 4.866. If you have any doubt like that, you can assume that is in triode and you can start comparing VDS less than VGS minus VT. You try to solve it and see the answer. This is getting wrong answer, this is getting correct statement. You just check it. VDS is equal to VGS minus VT. Comparison karke check kar. So 4.866 that is 4 plus root 3 by 2 is the correct answer. So that plus 3 will not impact anything. Don't worry about that. It will give the same impact for you. 70 thus here ID1, ID2 will be equal not due to regions. It is due to series. Any transistor can go in any region. But rule is here ID1 should be equal to ID2 because both transistors are in series. That rule you have to apply. Okay? Rule is not coming due to regions. Rule is coming due to series. Next question is question number 10. Question number 10. Try to think about question number 10. It's a very good question. Logical question as well. CMOS problem again. How to think question number 10? Try to see. Question number 10. Question number 10. So if you see this interesting question, question number 10. You have PMOS given. He has given a PMOS like this. It is some 10 kilo ohms. This is VDD. There is no arrows given in the problem. When they show like this, they will not give arrows. This is the way he has given. This is 10K, this is V0. So this is a circuit I am seeing. He's asking you output is what for this circuit. Carefully if you see, here there is no input given in the problem. Both are being coupled but no input is there. If there is no input, one simple common sense here. If there is no input here, automatically the current will go 0 here, no current. Here also, no current. Here also, no current. If there is no input, there is no current. If there is an input, you will get current. So can write this model once again like this. Yes, I can change the model like this. Simply, this is becoming short. This is your output. This is VDD. This model is looking like this. This became short because no current is there, because there is no input. So here input and output are becoming same here. This is input, this is output. Both are becoming same. because the resistor drop became 0 in the class. So correctly if you observe, this is not more than a trick of your MOSFETs. What is the trick here is, this is your MOSFET suppose, this is one MOSFET, NMOS. If you connect a short like this is drain to gate, we can say that your M1 is in current saturation. It is in current saturation. This is called NMOS. So according to the diagram, I think that is happening here. This is your drain, this is your gate. So gate to drain, you have made short. That's why this MOSFET is in current saturation. I can believe that. It is working under current saturation. And what about the PMOS here is? In PMOS, the source is top, and here he made short between gate and drain. They are short lengths. This is PMOS short circuit, gate to drain. This is also telling about M2, which is PMOS, saying that it is also in current saturation. So that means I understood that this MOSFET is working under current saturations. Okay? This is working under current saturation. This is also working under current saturation. If both are working under current saturation, I think where it is coming is when input is VDD by 2. When input is VDD by 2, we have seen the graph like this. Current saturation graph. Like this. This is threshold. Yes, roughly you can write. This is wave what? This is VDD by 2. So what is happening is, at this point, you have two threshold levels. This is one threshold, this is one threshold. You are having two threshold levels. Threshold, this is one threshold. One is PMOS threshold value, one is NMOS threshold output threshold values. These are your two threshold levels. That means here the switch is working under two threshold levels. So if you see the option there, answer is 0 volts is given in the first problem. Output is not 0 here. You have some value here. Threshold values it is working. VD of PMOS plus VD of NMOS by 2. That is wrong answer. And the last option D is VDD. VDD नहीं आ रहा इधर. हमको VDD less आ रहे. Some threshold voltage में आ रहे. So option D is said switching threshold of inverter. That means it is working under the switching threshold of inverter. So you can take this region. This region is switching threshold. It is working under switching threshold of inverter. So you can take this option. Switching threshold of inverter you can take. So C will be the correct answer for it. So I think 11th question you can try it yourself. Abhi teach kiya class. 11th question easily you can solve it. Saying that which transistor is in which region first to try to understand it. And ID1 is equal to ID2. Find out that answer. What is P0? You tried that question. Meanwhile, question number 11. Please write. 11th question. Bose is telling 3 volts is the answer for 11th. Any other students give me the answers? 11th question I think I will not do the question. You can do it yourself. Get me the option first. What is the answer? 3 or 2? Just check the answer for that. 11th question एक बार try करो. I'll take some water. Question. Question number 11. The arrows are wrong here. Typing mistake there. It's their NMOS problems. The arrow indications they have done wrong. Correct the problem like this. This is 5 volts. This is your V0. This is T1. This is T2. You take this as ID1. This is ID2. So both are current saturation. So T1 and T2 are in current saturation. Because both are short circuit. So simple thing. ID1 is equal to ID2. You do it and just find out the answer for it. Only Bose has given the answer. The other students try it and give me that answer 3 or 2. Two options are there, 3 or 2 which is correct. Just to justify that answer. ID1 and ID2 make it equal and see what is the answer for that. So I think V0 answer is coming how much? Only Bose has given the answer 3 volts. What about the remaining students? Finish that problem? Don't make me do that problem. It's a repetitive question again. So I'm waiting for some other students. At least 2 or 3 students if you go, I'll verify that answer. If it is 3 comes for everybody, we'll take the option 3. So I think nobody has given the answer. So only Bose has given 3. So blindly I'm believing him 3 volts. Okay, if any correction is there, you see that. I'm just believing him and I'm drawing that answer. So what about the 13th question? If you see the question number 13, he has given some graph, CMOS graph, saying that the graph is like this. CMOS graph. This is VIN, this is V0, this is VDD, this is half of the value, which is VDD by 2, this is VDD by 2. Okay? VI is equal to half of the VDD set. CMOS designed to have a midpoint of V1. Following VDD is 3 volts. UN Cox is given. UN Cox. Nu P Cox is given. VD VP. Now he's asking the ratio of W by L and to W by LP is equal to. So I think when you are exactly here, when the V1 reaches to here, the point, when your input reaches to here, we know that M1 and M2 will be in current saturation. Correct? M1 and M2 will come into current saturation. Therefore exactly you can write here ID1 will be equal to ID2. Both will be equal. So here half into UN Cox W by L1 into VGS minus VT whole square is equal to half into nu P Cox W by L2 into, here carefully write VSG minus VT whole square you write. Without having confusion, whatever you see here, you write the same answer in opposite manner, minus keep it like that, more or less, and find out the answer. Otherwise mistakes ho jayega, but carefully लिखो answer. So this is about the equation. I think he has given this answer, correct? This answers, these values are there with us. VSG is there, VT is there. So both have half of you can take, that is VDD by 2. So only thing is this ratio he wants, W by L1 W by L1 by W by L2. Just you have to solve this answer. So try to solve it. Yeah, I know that. This question, some students are giving 3 answers, some students are giving 2 answers. Yeah, I know that. Which is correct answer? 2 or 3. The question answer, some students are giving 3, some students are giving 2. So you try it here. This question is just current relation only. Carefully एक बार recheck करो. 3 or 2 confirm करो. Okay? So you just find out this answer. How much? Next question जाओ. ये try करके देखो. Otherwise एक बार my WhatsApp group में एक बार calculate करके देखता हूँ कितने आ रहे answer. So W by L1 by W by L2 find out करो that answer. So 13th question you can do it like this. And coming to 15th question. 15th question. Coming to the 15th question. Just by 6:30 we'll close the matter. Only 2-3 questions are there. So 15th question एक बार देखो. 15th question. 15th question he said that the MOSFET is a V0. This is your V1. This is your 5 volts. Carefully see here. This transistor is your V1. This is your active load. Correct? This is an NMOS inverter we call. This is an NMOS inverter. Active load. NMOS inverter active load concept. He said that the highest voltage here he has given 5. So can you use the common sense? This question actually we have to do the complete calculation. But this question generally in the exam point of view, they will not ask you to calculate all the things. I'll give just options for this. Because that will become a conventional question if you do the complete calculation. Yes, you should have a logical options for this. Suppose this is 3.5. This is 1.6 volts and 4.9 volts. And you can take it as 0.1 volt. By seeing these 4 answers, can you tell me which answer will be the appropriate answer for it? You have given input as 5. If the input is 5 for NMOS inverter with active load, how the graph you got? Just visualize it. This is your output. This is your input. How the graph you got? This is your threshold voltage. This is VDD minus VT, something we got disadvantage. Active load के लिए disadvantage आ रहा है आपको. So after this we have some linear line and bending to this point. The highest is VDD. VDD in this problem is 5. So that means your input, when the input reaches to 5, your input is given at 5. I think I have seen that your output is very close to 0 volts. It is not 0, it will be coming close to 0 volts. But common sense is enough to answer this question. These 3 answers are wrong. Your answer will be 0.1 volt. Okay? So this is called an invert observation. So in exam point of view generally, if you solve this complete analysis, it takes 1 page to calculate all the things because 1 will be in triode, 1 will be comes in triode, 1 will be comes in current saturation. You have to take both the equations and you have to solve it, quadratic equation. You get V0 result 0.1 volt. That will be the answer. Without having that imagination, if they give directly options like this, how to tackle the problem I'm telling you. Okay? Straightforward, take these options in the workbook and solve it. No need of doing complete calculation for that question. In conventionally, we can do all these twice. So we have question number 18. One question is there. 18th question. Question number 18 and question number 19. Question number 18 and 19. So let us understand question number 18, how to do it. 18th and 19th questions. So please complete that question 18 and question 19. 18th and 19th questions. So T1 will be easy only, T4 are easy questions. Only 18th and 19th, please cover it. The remaining questions are easy. 18th and 19th. So if I go to the 18th question, if you correctly observe the model here, he has given a PMOS. This is minus 5 volts and this is some 12 volts. Having some resistors here. This is ground. This is 10K. This is 10K. This is your ID current. So he's asking you how much is this ID current in the problem. And he said that Kn value is same for both the MOSFETs. NMOS and PMOS, Kn is same. And they said both are identical to each other. Kn is same means both are identical. W value is same. Kn value, that is UNC ox is same. Everything is same. But only the doubt I have is whether these MOSFETs are in current saturations or whether these MOSFETs are in triode region. If anybody asks you this type of question, simple logic here. We have used it here, a concept called biasing. Voltage divider biasing circuit. Whenever there is a biasing circuit there, compulsory the circuit will work in current saturation. So write down here. Voltage divider biasing. Voltage divider biasing makes the what is the transistor names he has given? You take this as M1, this is M2. Makes the M1 and M2 to be in current saturation. So straightforward you can tell without any testing. They will be in current saturation. So if this is in current saturation, whatever the current you will get, same current will come. So find out NMOS current. You can calculate for any current, NMOS current. If you take I is NMOS current, that is equal to half into nu n C ox W by L into VGS minus VT whole square. Just solve it. Simple problem it is. Simply if I think if there is no RS, you can call fixed bias otherwise. Okay? You can call fixed bias. Just have given a oral explanation that it is a voltage load bias. If you keep here RS, you call it as voltage load biasing. Otherwise, you can call fixed biasing. What is my meaning here is it is having biasing that I want to tell you. If there is a biasing in the circuit, no need of testing. Directly you can say that is in current saturation. Because here we cannot test it because VDS is not given in the problem. If VDS is not given, how do you solve the problem there? That's why voltage load biasing or fixed biasing. Fixed bias. anything is okay. Okay? If you keep resistor here, some RS, maybe it will become your voltage divided biasing, otherwise you can call fixed biasing. So answer, you can solve this one. How much it is? This total value is 0.1 milliampere per volt square. That half into UNC ox W value is 0.1. And the VGS value you can solve from here. This is gate voltage, this is VGS. So you can find this answer, VGS. 0 minus 5. 0 minus 5 minus threshold voltage given in the problem is 2 whole square. So answer is, so how much it is? Sorry, 0 minus of minus 5, it will become plus 5. So 5 minus 2 is 3 square. So 0.9 milliamperes. So 0.9 milliamps will be the correct answer for it. Okay, Sharnidas, your observation is good. A biasing can be a fixed biasing भी हो सकते हैं. In the exams, if you RS, it may be called voltage load biasing. Otherwise, you can call fixed biasing circuit. This is no problem. Biasing is there. That I want to tell you. It will work in current saturation straightforward. 19th question is a very interesting question. 19th question is an interesting question. Try to see. 19th one is a very good question. Try to see. This is the MOSFET here given. This is the M1. And we have another MOSFET. This is VDD. Short here. This is 2 volts. Like this here given a MOSFET M1 and M2. This is M1 and this is M2. So very intelligent questions. These are, try to see. He said that Kn value for this total two transistors Kn and how much he has given is, which is nu n Cox W by L for these two problems is two transistors is 1 milliampere per volt square given in the problem, and VDN is 1 volt. Carefully read the question one time. Lambda is 0, he said, is no need of channel length modulation effect. The minimum supply voltage VDD needed to ensure that the transistor M1 operates in saturation mode. Can you see that here? These questions are same like BJT classes. He's talking that this VDD you have to design in such a manner. This first transistor compulsory it should be in current saturation. That means EY's problem he's asking. Okay, it should be in the boundary he's asking. So what is the boundary equation here? First I'll try to understand. It want to be in current saturation. Your boundary equation is how much? You take here VDS1 is equal to VGS1 minus VD. It should be under this boundary because of M1 should be exactly in boundary condition. Okay. The minimum supply voltage needed to ensure that transistor M1 to be in current saturation. It is not asking to be inside the saturation. It's only under saturation is enough. So we're going to take our basic knowledge that VDS will be equal to VGS1 minus VD. Here if you see VGS1, this is your VGS1. It is 2 volts. So you can write here 2 minus. What is VD here is in the problem? 1 volt. This is 1 volt. So it is becoming 1 volt. So 2 minus 1 it is equal to 1 volt we got. Okay. There's a fill in the blank. No options are there. So up to here I completed my work. The next work I can do is, next work you can say this one is here. This is your VGS2 for you. And this is your VDD. Correct? Now the point is, this current is your ID2. This current is ID2. Can I say that it is 100% current saturation? M2 is already in current saturation biasing. So you can write here, M2 is in current saturation. Current saturation. Already it is in current saturation. So what we can do? ID2, we can write it as half into UN Cox W by L into VGS2 minus VT whole square. Just apply the current relation in the problem. Current relation I applied. Okay, current relation I applied. So can you find something from here? Is there any logic you can find from here that you have to think in the concept? Just I'm giving an idea for you how to do this problem practicing. Up to here I got the knowledge. Easily I completed the work. And actually this current and this current should be same naturally. This is your ID1 actually. So M1 boundary limit if you write, M1 is in H of saturation you can take. Exactly in H2 If it is in H also, we have the same equation, current saturation. ID1 is equal to half into UN Cox W by L into VGS2 becomes VGS1 minus VT whole square. I think we have two relations like this. From these two relations, what you can find, I'm thinking in the problem. I'm thinking in the problem what you can find. I think a VDD minus this value is VGS2. So let us equate these two things. ID1 is equal to ID2. Is there anything comes from this picture? Try to see. It is a half into UN Cox W by L into VGS1 will be 2 minus 1 whole square is equal to. This is 2 minus 1 whole square. 2 minus 1 whole square is equal to. Next half into UN Cox W by L into VGS2 we can write it as VDD minus 1 whole square. So this is 1 we got. VDD minus 1 is VGS2, threshold is 1. So just I equated like this concept. Can you see that this total term is balanced. So here 2 minus 1 whole square is 1. 1 square is 1 is equal to VDD minus 2 whole square. So VDD minus 2 whole square is equal to 1 we are getting. So we're going to find some value here. Quadratic value. VDD find out how much will be the correct answer. Just by that answer. You may get some two results here. Quadratic formula apply करके देखो answer. Already I think most of the students are giving answer there. 19th answer 3 volts is coming. 19th answer is 3 volts. So VDD you can have best chance is 3 volts. Okay, because this is already 1 volt here. Here 2 volts, it can be 3 volts. Maybe one answer will come 3, one answer will come 1 I think. If you get 1 that is wrong because the 1 is here already. You have some extra drop here, so you cannot take below 1 value or 1. You have to take above 1 value. So 3 will be the best answer for it. These are very good questions. So I think T1 question I'm leaving for you. T1 directly you can do it. All are in current saturation. The question you can do it. I'm not touching the question. Only the last T4 question is the final touch I'm doing for you. T1 I'm leaving for you. T4 will be the final question. T1 everybody can do it. Just see the W band ratios how much for each transistor. I want to do the final question is T4. I think these all questions have been covered in electrical book. You can This VDD is short. If you see clearly this circuit, it is looking just like a NMOS inverter with active load. This is an active load question. This is NMOS inverter with active load. He is saying that VDD is given in the problem is 5 volts and threshold voltage is 1 volt. Threshold voltage is 1 volt. He's asking you just a graph how to write. I think this graph we know the trick how to write is it's inverted graph VIN. This is V naught. Maybe the graph will come like this. Inverted graph, high to low. But common sense here, one logic I told you, it should be VDD minus VD. So whenever you talk about NMOS inverter with active load, there is a drawback in our notes that it will not give VDD highest value, it will give VDD minus VD it will give. Okay? Rahman here E by S, edge of saturation means the meaning is like this. This is your VDS, this is your ID, this is your graph, this is the boundary. VGS minus VD is the boundary. This is called edge of saturation, which have been created. You are writing in the message that VGS equal to VN is equal to VD. That is wrong here. This boundary is called as edge of saturation, we call. In BJT class, edge of saturation is 0.2. In MOSFET class, it is VGS minus VT. That is called overdrive voltage. Okay. Who is this? Saudinya, 16th, 17th. Saudinya, I think you have missed my class in previous workbook. Previous workbook 16th, 17th, I covered in biasing class. Previous video में cover किया वो देख सकते हैं आप. Saudinya, 16th, 17th, already I covered in easy book in the workbook of MOSFET biasing class. This is not MOSFET biasing class. Second module it is. First module में cover किया. Okay, in the recording video, please check it one time. So the answer will be here. It should be 5 minus 1. It should be 4 volts should be the answer. So I think it should be 4, not the 5. So D must be the correct answer for it. So anyway, successfully each and every question we discussed. So with this, happily I can end up this module. MOSFET is completed and BJT is completed on BC part. Total part is completed. So tomorrow and the day after tomorrow, maybe if requires next day for some time.